Good morning, good evening, good afternoon, and welcome to episode 3 or part 3 or I don't know, section number 3, segment number 3 of the training series, Neo4j training series we launched a couple of weeks ago with an intro and an intermediate cipher. And today we do a routing application with Will. Hello, Will. How's it going?
I'm good. Hey, Alex. Hey, everyone. Thanks for joining today. This should be fun.
It should be fun indeed. I'm looking forward to this one. We set the foundation sort of with the intro and the advanced or intermediate to advanced cipher stages, the last 2 episodes. If you missed those, don't worry. They are on YouTube. You can watch them at any other point in time and recap. Obviously, also this one will be recorded and on YouTube later on. So not a problem. But today we take it up a gear, a notch. I don't know. A level maybe if you stay with routing and elevation, I don't know, maybe and go into a little bit more advanced techniques and learnings today. So looking forward to this. There is a chat, so use the chat if you have any comments, any questions. If you just want to tell us where you're watching this from, obviously also interesting. Again, talking about maps and routes, it would be nice to see where people are living. So and are enjoying this training today. So we have that. There is a Q&A section as well if you watch this live on Big Marker, where our dear colleague Andreas is sitting on point to help with your questions. There he is in chat. So if you have anything, don't worry, don't be shy, don't hesitate, and let him know how we can help you. Obviously, we will also have some time for questions, so I will sift through a couple, and then we can answer a couple live on stage when we have a few minutes. So that is also the case. Recording, I said already, will be shared with you afterwards, as well as any slides we will go over. So yeah, I think that's more or less for housekeeping. Just as a reminder, though, before we dive in, this is, as I said, third kind of loosely connected string of a training series. There is another one coming. So if you are into Spring Data, Java environment, and how to work with Neo4j in this specific world, then on the 12th of April, so next week break, then back to training series. We have the Spring Data Neo4j episode, so in 2 weeks' time with Garrett. So if you're interested in this, please register, and I hope to see you there. But today, routing, maps, and all that good stuff with Will. So handing it over to you, Will.
Cool. Thanks, Alex. Yeah, I think that, comparing this workshop as the third in our series relative to what we've done so far, in the first introduction section, I think Michael did a great job of showing the different components of the Neo4j graph platform. So Neo4j Aura, working with the data import tool, Cipher, visualization with Bloom, and then Adam's intermediate Cipher session went a bit deeper into how to do a few more complex things with the Cipher query language. And today, we're going to kind of extend our universe, I guess, of understanding, the tools that we use with Neo4j, not just the Neo4j graph data platform tools. We're going to see how they work together to build like web applications, how to load data using Python Jupyter notebooks, and how to build a routing web app is, what we'll end up with today. So I would encourage you to follow along. We'll go through a few slides just to kind of set some foundation of some of the spatial functionality in Neo4j, which is going to be our focus today. So the slides are available, dev.neo4j.com /routing-workshop. You can also scan that QR code. Maybe I can put this in the chat easier for folks to grab. Or Alex, if you can put that in the chat for us. Cool. So I'd encourage you to open up the slides. Definitely, we want this to be, you know, as hands-on and interactive as possible. So, like Alex said, please answer any questions you have in the chat, and let us know how you're going as we're going through the workshop. We have, I think, 2 hours, and so we'll see if we can get our app up and running in the next 2 hours. So just a little bit about me. My name is Will. I work on the developer relations team at Neo4j. And so that means that my job is largely helping people be successful building applications, analyzing data with graphs and Neo4j. Best way to track me down is probably on Twitter or my website there. I have a blog and newsletter that you can check out as well. And again, link to the slides. We'll see those a few more times before we get started. So the idea for this workshop started out, I don't know, a few months ago. I was looking for different ways of working with OpenStreetMap data in Neo4j. And we'll talk a bit about that in a minute, what that means. But really, you know, I wanted some way to test different OpenStreetMap data models and data sets that I was using. And so I built this routing application that just allowed me to search for points of interest or addresses and then view the shortest route between them. And as I went through that, you know, there are some cool, useful things that we touch on. So like how to use the Neo4j JavaScript driver in a web application to send Cipher queries to Neo4j, how to use a full text index to do autocomplete address or point of interest search. So I thought, you know, this might be interesting for others to share. So just kind of asked on the Twitter if that was something people would be interested in, and a few folks said yeah. So we built a workshop around it and scheduled it for today. So here's what we're going to build. It's a fairly simple web application, but basically what we want to do is be able to search for addresses or points of interest. And, you know, we want this nice autocomplete search feature as we start typing in an address, you know, giving us this, you know, drop down list of possible matches so we don't have to type out the full address, things like that. And then using graph algorithms to plot the shortest path between our two points of interest or addresses. In order to get there, we're going to work with data to build our road network from OpenStreetMap. We'll use Leaflet.js, which is a JavaScript mapping library for creating web and mobile maps. And of course, we're going to use Neo4j and Neo4j Aura. So there's basically three, we call them modules or sections that we're going to work through. The first one is going to be, you know, a brief overview of Neo4j and Cipher, but really with a focus on the spatial functionality in Neo4j and Cipher. Then we're going to take a look at how do we work with OpenStreetMap data in Neo4j specifically. So we'll talk about OpenStreetMap, a couple of different ways of getting data into Neo4j. We'll see what we can do with that, routing, querying, that sort of thing. And then we're going to build our web map with Leaflet. Along the way, we'll use some of the tools in the Neo4j graph data platform, like Neo4j Aura, Neo4j Bloom for visualization, things like that. So, like I said, we do want this to be as hands-on as possible. And so we will use this icon here where it says hands-on exercise. We'll use that on the slides to indicate, you know, when we want to make sure that folks are following along and, you know, doing some of the exercises. We will be using Python and a little bit of JavaScript and HTML. My suggestion would be to use GitHub code spaces for this. We'll we'll take a look. That's what I'm going to use. I tested it last night, and everything worked fine in the CodeSpace environment. So it would help to have a free GitHub account. If you have a local Python development environment and you're comfortable with installing packages and things like that, you can certainly clone the GitHub repo and work locally. It's up to you. We don't have time to troubleshoot a lot of installation issues and things like that. So that's why I like CodeSpaces, and that's what I'll be using. Pretty neat feature. It gives you a sort of VS Code development environment through GitHub in the browser, which is pretty neat. So the GitHub repository, so all the code we're going to use today lives here. We'll drop in the chat as well. And there are basically two, you can see in the README kind of an overview of what we're going to do today. There's two main pieces to this. There's the notebooks directory that has a couple of Python notebooks, and I'll zoom in a bit here. Easier to read. Maybe too much. There we go. So we're going to run these notebooks to connect to our Aura instance. This is just kind of a sanity check one. In the notebooks directory, and then in the web directory, we have some HTML and JavaScript. These are going to be our simple web app code for our web map. So that's the code we're going to work through. Definitely have that open up in a tab as we're going through. So what are the prerequisites? I think if you have some basic familiarity with Python, that's good. Not required. We'll use sort of a lot of skeleton code to get us started. We will use Neo4j Aura DB. We're going to use the free tier, so you can sign up for a free account on Neo4j Aura. We'll go through the steps to do that and create our free tier database, but we will be using that. Cool. And just a couple of resources as we go through this. Cool. So let's go ahead and jump in. And again, feel free to ask your questions in the chat, and we will be sure to address those. Let's talk about overview of Neo4j, but really with a focus on spatial functionality in Cipher, which is the query language that we use with Neo4j. But I guess to kind of motivate our workshop today, I like to talk a bit about my sort of realization that graphs are really powerful and relevant for working with geospatial data and in GIS, that's Geographic Information Systems. And when I was first learning about GIS and in geography, Tobler's first law of geography really stood out to me. So this says that everything is related to everything else, but near things are more related than distant things. So, for example, I was in Minneapolis for a conference a little bit ago, and we could compare Minneapolis to some cities in California, San Mateo, San Francisco, and so on. And we can say that, San Mateo, San Francisco, these cities in California, they're more similar to each other than, say, San Mateo is to Minneapolis, because San Mateo and San Francisco are nearer, both in terms of distance, but also probably culturally. And I think Tobler really intended this to be measurements not just of distance, but other measures of similarity, like cultural, human geography aspects. But distance is a good way to think about this. But we've seen this before, and like we can quantify these distances. Like this is a graph that Tobler was talking about, this first law of geography. So I think this example to me like really highlights that graph thinking is really foundational to even geospatial and geographic data. But let's take a step back and think about when we're talking about a graph, what are we actually talking about? What do we mean? Well, fundamentally, a graph is a data structure. So nodes, these are the entities, relationships, connect nodes. And when we're working with graph data, we need the ability to store arbitrary key value pair attributes on the node or relationship. We need some way to group the nodes to describe the type of the node, what kind of thing it is. Those are node labels. And then similarly for relationships, we need some way to describe the type of relationship. That's called a relationship type. And this data model, this is the property graph data model that graph databases like Neo4j use to allow us to model, store, and query our data as a graph. So let's look at an example of a property graph. So here we have some information about news articles. We have the topics, the people mentioned, the geo regions that the articles are about, kind of extracted out into nodes. And this is a good example of what's called a knowledge graph. Knowledge graphs just put things in context. So we have some canonical representation of this topic node, US politics and government. So then we have another article that comes in, we know to connect it to this topic node. If the article is about that topic, we can then traverse the graph to find what are all the articles about this topic that mention the geo-region China, and so on. So this is what Neo4j allows us to do fundamentally, to model, store, and query our data as a graph. There are lots of interesting pieces to the Neo4j graph data platform, things like the Cipher query language, different tooling that we'll use like Neo4j browser, Bloom for visualization, Aura, database as a service. But fundamentally, we're interested in modeling, storing, and querying our data as a graph. And with Neo4j, we use Cipher to do that. You can see an example of Cipher here in kind of the upper right. And you can see Cipher is really all about this idea of pattern matching. So we draw these sort of ASCII art representations of the graph, nodes with parentheses, relationships, square brackets to sort of indicate this graph pattern that we're looking for. And we'll do quite a bit with Cipher today, so it should be fun. So that data that I showed earlier, the example of the knowledge graph with our news articles, that comes from the New York Times API. So I have a little process that goes out and scrapes the day's most popular articles from the New York Times API and loads it into Neo4j. If you're interested in that, the code is linked here on GitHub. But if you think about, once we have our data loaded in Neo4j, there's really this kind of spectrum, I think, of graph access patterns from the local traversal, where I have a well-defined starting point. Maybe I'm starting from, I don't know, the Joe Biden node in my news graph, and I want to traverse out to find all news articles or topics associated with articles about Joe Biden. That'd be example on the left here of the local graph traversal, where we have our well-defined starting point and we're traversing the graph from there. But then the other end of the spectrum are these graph global operations. And these are typically things like graph algorithms where we're interested in the structure of the entire network, or these iterative graph algorithms like PageRank, where we're sort of moving through the entire graph to find who are the most important nodes in the network. Can we cluster the network into different communities based on their structure? And I think a lot of applications, our access patterns kind of fall somewhere in between the spectrum. Often we're combining graph global operations with our local traversal. We want to factor in PageRank into our article recommendation feature. these sorts of things. But this is at least my framework, I guess, for thinking about this. Okay, cool. So let's talk about some of the functionality for working with geospatial data in Cipher. So Cipher and Neo4j support a native point type. This is kind of the foundation of working with geospatial data in Neo4j. And the point type supports 2D or three-dimensional, either geographic or Cartesian coordinate reference system. So for geographic, this is data. This is like longitude, latitude. Cartesian would be, kind of XY, where the units are whatever you want them to be. With geographic data, the units of longitude and latitude are decimal degrees. We're not going to talk about Cartesian data today, since we're interested in geospatial data. So we're going to focus specifically on two-dimensional WGS84 or geographic data. So think latitude and longitude. And we can store points as properties on nodes or relationships. So here's just an example. We're creating a point of interest node. Again, notice this, these parentheses that indicate we're sort of drawing a node pattern. And then we set a few properties. We set the name of this bakery and its location by specifying latitude and longitude. So some of the spatial functions in Cipher, the point.distance function, this is a core function for spatial search. So being able to find things near other things, compute the distance between things. Here we're doing essentially a radius distance search for any points of interest within 200 meters of a certain latitude and longitude. Going back to our New York Times news graph, we have these georegions. We don't actually get the latitude and longitude, though, from the New York Times API for each georegion. We just get some text description, like this article is about China or the United States or California or San Mateo. So what we can do to add that information is what's called geocoding. And in Cipher, we can do geocoding with the APOC spatial geocode procedure. If you're not familiar with APOC, it is the standard library for Cipher that ships with Neo4j that adds some additional functionality. There are lots of things in APOC. We're going to use APOC today for some of the routing functionality. So we'll see APOC also for some of the data loading. We'll see how to work with GeoJSON data using APOC. But anyway, geocoding is one of the things we can do in APOC. And what that means is we have some textual description of a location. So this case, Union House, London. This is where Neo4j London office is located. And the spatial geocode procedure will go out to one of the geocoding APIs and figure out the latitude and longitude of that point. We can then incorporate that into our data import workflow. So here's the example from how I import that news graph. I GitHub Actions to do that. It's easy to schedule cron jobs. But basically, after we import our news articles for the day, we find any geo nodes that don't have a location, geocode them, add the latitude and longitude as a point property on the node. Then that allows us to write queries like this. So here we're searching for all the news articles that are about any georegions. In this case, it's within 200 kilometers of a certain point. This is somewhere in Montana. So here's all the news about Montana. It's a little sparse for the New York Times. It's not a regular beat, I suppose, for that area. But you can see how we traverse the graph to find articles in the geo, topics of those articles, and we can really construct any arbitrarily complex graph pattern at the top here in Cipher to traverse this data. starting from any of the geo regions that are within a certain distance of our area of interest. That is the starting point for our traversal. We're talking about these local traversals where we have a well-defined starting point. In this case, the geo node, because we're filtering with this where predicate on geo nodes within a certain distance of this point, become our starting point. And then this graph pattern we're describing up above, we're traversing the graph from those geo nodes as our starting point. Cipher also has some pathfinding functionality built into it, which we're of course going to leverage today for routing. So for example, if we wanted to find the shortest path between two nodes in the network, we could use this shortest path function, which is built into Cipher. So here we're searching for the shortest path connecting two government organizations. And here we're using the variable length path operator. That's the asterisk here in Cipher. And that means find where this path exists, where these two nodes are connected, but follow any number of relationships to get there, up to, in this case, 100. It's always a good idea to set an upper bound on this, just so we're not unnecessarily searching super long paths if we know we aren't interested in those. The shortest path function, which we'll see later on, uses a bidirectional breadth first search. So we start from each of our in nodes and sort of work to connect them using a breadth first search. Note that this means it's the shortest path based on the number of relationships, not necessarily shortest path based on something like distance or time traveled. We'll see how to deal with that in a moment. Okay, so we saw the basic sort of point functionality. That's sort of the core of working with geospatial data in Cipher. I want to go through some options for spatial search. I'll go through this fairly quickly, since this is not immediately relevant to what we're working on today, but I think these are important concepts to understand. So we've already seen radius distance search. This is that point.distance function where we're searching for things within a certain distance of some point. We can also search for things within a bounding box, or even within a polygon, which is a common use case. So these examples use data from OpenStreetMap point of interest. There's a link there to the code to import those. We're just using that as an example. We're going to work with some data from OpenStreetMap in a minute here. But one thing that's important when we're working with non-trivial, like larger, medium-sized data sets, is to create a index, and specifically a point index. So creating a point index on the location property on our point nodes, this will allow us to do faster lookups. So our radius distance, our bounding box search, those are going to use an index rather than scanning every node in the database, computing the distance, these sorts of things. We have an index data structure to be able to find those efficiently. It's always a good idea to make sure that your indexes are online. So below, we called the :schema function in Neo4j browser. And we can see that this index is still populating, so it's not available to use. After a minute or so, it comes online, and then we can use it. And to understand like some of the differences and why creating an index is important, here's an example. So this is the same query, one using an index, one not using an index. So I just add the profile keyword here to get what's called the query plan. This is a good way to do query tuning with Neo4j. And on the left, we can see we did not use the index. We did a total of 49 million database hits. I think our data set size, I think this is like 18 million or so points of interest, somewhere in that ballpark. And on my laptop, it took just under 4 seconds. But if we do this using an index, we're only doing 213 database hits in 1 millisecond. So you can definitely see the difference there and some of the performance implications. So always use an index for these spatial search functions where we can. Okay, so that's radius distance. Bounding box, if we know the lower left and the upper right coordinates, we can pass those to the point dot within bbox Cipher function, which will find all points within that bounding box. That will use an index as well. This actually is somewhat more efficient than a radius distance search because the index that a radius distance search is using is basically a bounding box and then post filtering to find everything within sort of that radius circle. So the within bounding box directly use the index without that filter operation, if that makes sense. And then the other type of spatial search that is pretty common is the point in polygon search. And I think the best way to do this using the database index in Neo4j is first to convert your polygon to a bounding box. You can do that on the client, and then send the within bounding box query to Neo4j to leverage the index, and then filter your results on the client to within that polygon. And there's a link here to an example of that using turf.js, which is a JavaScript geospatial package. Okay, so we've talked about point geometries. Of course, there are more complex geometries in the world, things like lines and polygons. And one way to work with more complex geometries is to store your coordinates as a list of points. So here is my Strava data that I imported from my Strava export. And we can see here the interesting piece here that I want to show is basically grabbing all of the points that make up a line, since a run or a hike or a walk in Strava is a line geometry, right? A series of points. We can collect those into a list and store that as a list of point coordinates, which we can then use the list predicate functions like any in Cipher to still do our spatial search on more complex geometries. So this basically will find any geometry nodes where the coordinates, which is a list of points, or any of those points within that list are within a radius of this point. So you can see here we found this. I think this was a jog that I went on out to this park. These points are within our radius. These are not, but we still find that because at least one or more of the points was within that radius. Okay, let's talk about routing. So for routing, so finding the shortest path between 2 points, we use pathfinding algorithms that are kind of a subset of other graph algorithms. So we put graph algorithms in this category. Things like centrality algorithms, community detection, clustering, node similarity, machine learning. These are all found in the graph data science plugin for Neo4j. We're not going to use graph data science plugin today. We are going to use some of the pathfinding algorithms that are available in APOC, but they're also available in the graph data science package. So a couple of different ways to approach that. This is an example of using routing with the graph data science plugin. I want to show how this works, and then when we get to the hands-on section, we'll see how to do this with some of the functionality in APOC. But imagine we have a graph of airports. Airports have a has-route relationship between them to represent flights between those 2 airports. With GDS, the graph data science plugin, the way that we work with data is by first projecting it into memory. Since these algorithms run in memory, we need to project the graph that we want to work with into an in-memory graph. And the reason we do that is because oftentimes the graph that we want to run our algorithms on is different from the graph we've actually stored in the database. Maybe we want to run algorithms on inferred relationships that don't exactly exist, or sort of closing of like triangles and things like this. In this case, we're loading the airport connected to airport through the has route. That's what this syntax is saying. So load just the airport to airport piece of our graph, load that into memory. We want to factor in distance, which is a relationship property on the route between each airport. And then we can use, in this case, the GDS shortest path Dijkstra. So this is Dijkstra's algorithm, which is the shortest weighted path. And here we're routing between, it says Punta Arenas in Patagonia and Honolulu. And so we can see by distance the shortest path between these two cities or through these airports. Okay, cool. So that was a super quick overview of Neo4j and Cipher. The next step is we're going to get hands-on and jump in with Neo4j Aura. But maybe I'll pause for a second there and ask Alex if there's any questions from the chat that we should maybe dive in on before we get into the hands-on section. What do you think, Alex?
Yeah, there was one question which is probably interesting. Is there was an old spatial module a while ago, which was before the time that spatial functionality was a part of Neo4j, and William has a side project at using that, but he's not able to get it working anymore. Is there I think code has changed. There's probably not a direct linkage between the two implementations. Do you know?
Yeah, that's a great question. So I think you're talking about this project, the Neo4j Contrib spatial project. Yeah. So this for a long time, I think, was the best way to work with geospatial data in Neo4j. Craig Travner is the main developer who worked on this. And what this did, it added a lot of spatial functionality to Neo4j through the plugin architecture, and then later on added spatial procedures and things like this, so we could use Cipher extensions in Cipher to work with spatial data. And it did things like build an in-graph R-tree index rather than the native spatial indexes before those existed, and these sorts of things. So I think some of the functionality in the spatial plugin now exists native in Neo4j. There's a 4.4 release, you can see is the latest release. If you're using Neo4j version 5, I saw a pull request come in updating to version 5 in progress. That there's not a release on that. So I think it depends on what you're trying to accomplish. I would encourage you to see if you can accomplish what you want to with the native functionality in Neo4j instead of using the spatial extension, because it's a little bit behind the latest Neo4j releases, and duplicates some of the functionality there. But if you're stuck on something, I would suggest opening a thread in the Neo4j community site, community.neo4j.com, and just kind of describe what you're trying to do and what's going on, and folks will hopefully get you started there.
Yep, cool. And then maybe we take this under one question from Deep. anything to worry about them in-memory limitation as data scales in relation to projections of the graph for the GDS use cases?
Yeah, for GDS, I mean, those are in-memory algorithms. You're going to want a machine with a lot of memory to work with that. There are some optimizations and things like that for working with data in memory that the GDS library uses that I'm probably not the best person to talk about. But yeah, I think what you can do with any of the algorithms, there's a like memory estimation version, I think, of every algorithm. So you can, sort of like before you run it, check to see how much memory is needed to run that algorithm on that data. So I would start there and sort of see, what you're looking at in terms of resource requirements, if that makes sense, if that's more than you're expecting. But yeah, I would start there with running that estimate procedure to figure out what kind of resource requirements you have for your data.
Yep. Okay, that makes sense. That's it for now.
Cool. Let's jump in then to our first hands-on piece, which is going to be setting up Neo4j Aura free tier. So we're going to go to Neo4j Aura and sign in and create a free tier database instance. So I'll go through this now, and then we'll pause for a minute or so to make sure folks are set up. So I'm going to click here on Start Free. So Neo4j AuraDB is Neo4j's hosted database as a service, and so because it has a free tier, it's quite nice. We can spin up instances that, unlike Neo4j Sandbox, if you've used that before, Sandbox instances go away after a few days. Neo4j Aura instances, even the free tier, those ones stick around. So it's nice for building hobby projects or small projects like this one. So I just signed in to Aura. You can sign in with like a Google account or create a new account with email address. And we're going to go to new instance. And there are a bunch of pre-populated data sets. We are going to load our own data. So I'm going to select the empty instance. And I get this screen, which shows me the credentials. So we can copy our password, but if we click download, that downloads a .env file, which has our database credentials stored locally in it. So we want to make sure we download that, copy the password as well to be double secure, because we cannot recover that once we click continue. And so this is going to spin up our Aura free tier instance. It'll take a couple minutes to spin up. Cool. So if you want to follow along, go ahead and spin up your Aura instance. Pause maybe for just a minute or so, just to give you kind of an indication of where we're going after this. Once we spin up our free tier instance, we're going to talk a bit about working with OpenStreetMap data, and then we're going to get our Python development environment set up and start importing some OpenStreetMap data into our Aura instance using our Python notebook environment. Okay, yeah, and you don't need to get any further right now than just this screen. So if you see creating instance with a spinner, you're good. Cool. Let's talk a bit about OpenStreetMap while we're getting our Aura instances set up. So OpenStreetMap is really this amazing data set. I'm kind of amazed that this exists. If you've used OpenStreetMap before, let us know in the chat, especially if you're using it with Neo4j. I'm very curious what your uses for the OpenStreetMap data are. Basically, OpenStreetMap is a crowdsourced open repository of map data of the world, contributed by individuals that are mapping certain areas, but also there are lots of corporate contributors as well that rely on OpenStreetMap for their mapping software. So like Facebook is a big contributor to OpenStreetMap. They use OpenStreetMap as the base for all maps on the different Facebook platforms. Microsoft recently contributed a bunch of machine learning applications. So using machine learning to identify things like roads and satellite images, contributed that back to OpenStreetMap. So it's really a valuable and well curated data set, but there are also various services and tools built around OpenStreetMap. So things like map tiles, a geocoding server, vector data of buildings, road networks, these sorts of things. And OpenStreetMap data, we can download OpenStreetMap data directly or access it via OpenStreetMap's, it's called Overpass API. So let's talk a little bit about the data model in OpenStreetMap. So the main entities are nodes, ways, tags, and relations. So nodes, these are point features, and this can be points of interest, or they can be just nodes that are part of a more complex geometry, such as a line feature. And that's what ways are. Ways are line features. So these are features that connect nodes. So ways are made up of multiple nodes. And ways can represent things like a road, or things like a building footprint. So that would be a closed line, so like a polygon geometry, or boundaries of a park, these sorts of things. And then the tags, these are the key value pair attributes that describe these features. And we can use these on nodes, ways, or relations, which I'll talk about in a second. Basically, the tags are, let's go back to this example of San Mateo. So you can see the different tags that we have for San Mateo. So San Mateo is a county in California, and you can see the different tags associated. So the population, the source of that population, the type, it's a boundary, a Wikidata ID that connects it to information on Wikidata. So you can see there's lots of kind of freeform tags to describe our entities. And then relations are the other sort of entity type, and these organize multiple ways or nodes into a larger entity. So like an example would be, multiple road segments that make up a bus route, or this is how multi-polygon geometries are represented in OpenStreetMap. So a multi-polygon is typically can be like a polygon with maybe a hole cut out of it represented by another polygon. And so relations are the ways to group, in this case, multiple ways that describe multiple polygons. There's lots of good resources out there on kind of working with this OpenStreetMap data model. But this should be no surprise. Like this is a graph. We're describing nodes, like these points, and how they're connected to form more complex geometries, and how those ways are connected in relations to make up more complex things like the bus route example that we talked about. So it makes sense naturally that we would want to work with this data as a graph. And of course, there's been some interesting work done working with OpenStreetMap data in Neo4j. So here's a couple of examples. The one on the left, this is a screenshot from the OpenStreetMap Neo4j sandbox example. So this is a pre-populated data set that we built using data from OpenStreetMap data from Central Park in New York City. So there are points of interest, there are walking paths and the road network for basically everything in Central Park. And it walks through a few examples of how to find different points of interest, how to do routing. I had a fun project on the live stream it's probably a couple of years ago now, or at least 2 years ago. We built a travel guide example app. That's what the screenshot in the middle is from, using this sandbox data. And basically, we wanted to pull in things like information from Wikipedia and Wikidata, images. These come from Mapillary, which is really cool, user contributed kind of street view photos and things like that. So if you're interested in some examples of working with the full OpenStreetMap data in Neo4j, there's some pointers here. These are based on a OSM data importer for Neo4j project. Another one that Craig, the gentleman who created the spatial extension, also worked on. So if we go back though and look at this data model, can I zoom in a bit? Yeah, no, sort of. It doesn't really work. You can see here there's a lot going on. Like we're modeling the exact data model from OpenStreetMap of nodes, ways, relations, and tags. And then we've added things like point of interest, intersection, and it's such a rich data set, OpenStreetMap, but depending on your use case, depending on what you're trying to do with it, maybe you're not interested in every node that makes up a street, a road segment. Maybe you're just interested in the road segment between intersections, and certainly if you're interested in routing, that's typically the case. And so, what I've been interested in more recently is working with a more simplified OpenStreetMap data model. So in this example, we had to go through and identify the intersections and tag those as things that we can route between, sort of overlaid on top of modeling every node in the OpenStreetMap data. But really, if we're interested in routing, we're interested really in a graph that looks like this, where we're connecting intersections with a road segment relationship. And this simplifies things quite a bit for us. It significantly reduces the data size for working with OpenStreetMap data. But perhaps more importantly for people trying to actually build things is that it simplifies our queries. And so now if we want to do routing, we can just route between intersections and this road segment relationship, much simpler than trying to work with the more fine-grained OpenStreetMap data model. So this is the data model we're going to use today, and build on it from there. We're going to use the OSMNX Python package to import data from OpenStreetMap, or say rather to fetch data from OpenStreetMap and then import it into Neo4j. OSMNX is a Python package for fetching data from OpenStreetMap and building road networks specifically. So it comes from the University of Southern California Urban Planning Lab. So they're interested in being able to analyze road networks. And there's a couple of really important features that it has that I think are really nice. One is that we can search OpenStreetMap through the Overpass API directly through OSMNX. We type in like the location we're looking for, OpenStreetMap geocodes that, and then OSMNX builds a graph structure of the road network And it will specifically simplify the topology of the road network. So you can see on the right, only the intersections become nodes in the network. And this is a significant simplification of this data model, where we're modeling sort of each point, each observation for each way. So this makes it really, really nice to use OSMNX to get these sort of cleaned graph data structures for working with road network data. Okay, cool. Let's jump into our Python environment and start working with OSMNX and Neo4j. So in the GitHub repository, there are a couple of notebooks. We're going to start with the 00 setup IPyNB. And basically what we're going to want to do is open that up and put in our AuraDB connection credentials to run some queries against Neo4j. Initially, we're just going to make sure that we can use the Neo4j Python driver with our Aura instance. Then we'll move on to a more complex example of actually importing some data. So I said earlier, and I'll link the GitHub repository again. I said earlier that you can use a local Python development environment or something like Google Colab. I think the GitHub code space environment is, for a workshop, a really good option. It's going to install our dependencies for us, so we don't have to worry about that. So I just clicked on, I'll show that one more time. What I did was on the repository page, you can fork this if you want, or I think you can just run it from here. And Codespaces is now free for everyone. And I clicked on load Codespace, and so it gives me this VS Code like environment. You get some initial setup. Here's the terminal. So it's going to detect that we're working with Python. It's going to install some Python things for us. We're using Poetry in this project to define our dependencies. So here we can see our dependencies are basically Jupyter for the notebook environment, and then Neo4j, which is the Neo4j Python driver, and OSMNX. And so you can see now Codespaces is installing those dependencies for us, which is quite nice. So what we want to do is go to our notebooks, and let's start with this first one, 00 setup. Yes, we will install recommended extensions for Python. Cool. Oh, and if you get if you lose the file explorer, which happens to me, you can do Command-Shift-E to bring that back. Codespaces gives you a VS Code environment. So if you use VS Code, the VS Code key bindings should work for you. Cool. So here's our notebook. Let's get the terminal out of the way here. So all we want to do in this one is make sure that we can connect to our Aura instance and use the Neo4j Python driver to execute a Cipher query. So because we're in the Codespace environment and we specified our dependencies in that Poetry package file, Neo4j is already installed for us. But pip install Neo4j is how we would install that. This part is kind of tricky. We do need to select a kernel to run our notebook, and we specifically want that Poetry kernel, the one that Codespace selected for us. It should give it to us that by default. I don't know why it does, but what we want to do is click right here where it says select kernel, and then we're going to choose Python environments. And rather than the recommended one, I'm going to use this one that says Poetry env. So this is our virtual environment that's created that specifically has our dependencies installed from that Poetry config. So if you don't select the Poetry one, then you will have to do this pip install. Okay, so I'm going to run this cell, import Neo4j.
What was the shortcut again to bring back the Explorer? The
Command Shift E.
Command Shift E. All right. So, thank you.
Google, yeah, my search last night was how to close extension panel. But no, if you search for VS Code keyboard shortcuts, this one? No, that wasn't one. There's a page that has like pretty good overview of the different shortcuts. But yeah, that Command Shift E was the one that tripped me up for a while. Cool. So we ran this cell, imported Neo4j. That means we've got our dependencies installed. That's great. The next thing we need to do is connect to our Neo4j Aura instance. And so I want to find my .env file. Here it is. So here are my Aura credentials. I'm going to copy these. Actually, let me move this off screen. So we'll grab first our URI. And so yours will be different, but this basic format. This first part, Neo4j plus S, that protocol. This means use the Neo4j protocol. Plus S means I want a secure connection. And this was the URL for my specific Aura free tier instance. The user is going to be Neo4j by default. That's the user created for us, the database user created for us. And then our password is going to be random. And again, yours will be different. And then we run that cell. We're creating a driver instance connected to our Neo4j Aura instance. And then here we have a pretty simple Cipher query that says match in, return count of in as node count. So this is just saying we're going to find all the nodes in the database and return a count of them. Then we're going to define a function to execute the Cipher query. And we're specifically using what's called a transaction function. So there are a few different ways of using the Neo4j drivers. If we're doing something kind of simple locally, we can kind of get away with the session.run kind of implicit function. But once we start working with instances, over the network, it's a good idea to use transaction functions so that we have things like automatic retries and these sorts of things. So transaction functions give us that functionality. Notice here also that I get back a result set from executing my Cipher query, but then I can easily convert that to a data frame. So a data frame is a Python data structure for working with tabular data in Python. And this is really common to want to get data into a data frame structure. So this toDF method on a Neo4j driver result set will give us a data frame. And then we're going to create a driver session. And the session really represents some unit of work that we want to do with the database. It doesn't quite map one-to-one to a connection to the database because there's some connection pooling going on. But basically, think of you want to create a session anytime you want to do some given body of work with Neo4j. And now we should have a data frame with one row, node count of 0, because our database is empty. There's no data in there, so this is what we expect. So this is just sort of a proof of concept sanity check that we can connect to our Neo4j Aura instance. So you should get results just like this: node count 0. If you get an error, make sure that you've put in your database credentials and that dependencies are installed and so on. Cool. So the next thing we want to do is move to the next notebook to actually import some data. But we'll pause here if there are any issues that folks are having before we move on to the next session. Cool. Let's look at the next notebook.
Yeah, I think we can continue. I see no immediate questions.
Cool. So our goal for this notebook, so I moved to 01 import. Our goal in this one is to import data from OpenStreetMap to build this routing graph, this graph of intersections in Neo4j. And so now we're going to import both Neo4j and OSMNX. And again, we need to select our kernel. So if it prompts us, we can go to select another kernel, or the way I get to it, if I remember to click on it, is select kernel, select another. We want Python environments, and then we want this one associated with our poetry environment. And we know we have the right one if we run this import cell and we don't get an error, which means those packages are available. If they're not available, if you're using local environment or Google Colab, you can just uncomment these two pip install lines and run this cell. Cool. And then I'm going to go back to my credentials here from the previous notebook. I'm just going to copy these and paste over here. We could also set these. I have this set up in a to read from a .env file. We could set our environment variables here and then read these as environment variables. That's perhaps a better option, another option. Okay, we'll run this cell again to create a driver instance. And so what we want to do now is search OpenStreetMap and create an OSMNX graph. So I'm going to run this cell. This was taking like 40 seconds for me when I was going through this last night. So it'll run for a minute or so. So what's going on here is we're calling this graph from place method on OX, which is the OSMNX module. And we say we want to drive networks. This is going to go to the OpenStreetMap Overpass API and pull in the road network for San Mateo County in California and go through that topology simplification process. So pull out only the intersections and model that as a network X graph. So network X is a Python package for working with network or graph data. So this is where the name OSMNX comes from. It's OSM for OpenStreetMap, NX for network X, because we're working with network or graphs of the road network. You should see a plot like this. This is the San Mateo Road network. If you're not familiar, this is the coast here. So like Half Moon Bay is here, and then there's some mountains to go over, and then this is kind of downtown San Mateo here, and then what is this? Is this where the bay is? I think that's right. Okay, so we have this this network X representation. What I want to do is convert our network X representation to two geodata frames. So a geodata frame is like a pandas data frame, but adds some specific functionality for working with geospatial data in a data frame. And so what we've done here is just pull out two geodata frames, one for the nodes and one for the relationships, and we can plot those. So here's our nodes geodata frame, and we can see that every row represents a node, which you said was a point geometry, and specifically in this case, it represents a intersection because we've simplified the topology a little bit. So we have a point geometry for every node. We have some tag information, like the number of streets in the intersection, is it a highway, and so on. And the OSM ID, so the ID value. And then we plot all the nodes a little bit just to kind of see what that looks like. And then we can do the same thing for our relationships geodata frame. So the relationships, these are going to represent road segments between intersections. So their geometry is a line string or a series of points. Those are intermediate points that represent the road segment connecting the intersections. Here you can see we have things like the speed limits, if it's one way, how many lanes it has, these sorts of things. And here's the plot of just the relationships. Okay, so we've got that data in Python. Let's load this into Neo4j. So here are a few queries that we're going to run. So the first handful are creating database constraints and indexes. So constraints are important, I should say specifically property uniqueness constraints are important to create when we're importing data if we are using the merge Cipher command. So merge is like an upsert, like a get or create operation. And creating that constraint will allow us to make sure we don't create any duplicates. We don't want to create any duplicate intersections. And we have this OSM ID that we know is a unique identifier for our OpenStreetMap nodes. We'll also create an index on the OSM ID for the road segment on the relationship. And then we're going to add addresses in a minute. So we'll do that also for addresses. And then we'll create a point index for the intersection location, which we'll use when we start hooking things together and doing some routing. And then we have two Cipher queries to load each of the geodata frames, one for the node geodata frame and one for the relationships geodata frame. For the nodes, so what we're going to do, and this is one of the main reasons we converted our data structure into these geodata frames, is that we're going to batch our data frames into a number of rows that we're going to pass to the Cipher query as this rows parameter and then unwind over them. This is a good technique to get pretty good throughput in Cipher import statements if we unwind over an array of data and then do some operation on that. So we're going to merge, creating intersection nodes for each row in our nodes geodata frame. And then once we've done that, for the relationships, we're going to find the two intersections that correspond to a road segment and connect them using a road segment relationship. You can see this UV maps to how our relationship geodata frame is indexed. The U and the V, the from and the to are the node. The OSM IDs for from and the two intersections. Cool. So execute that cell if we haven't yet. And then just like we saw previously, where we were defining a function to execute our simple Cipher query, we do that for, these are all of our constraints together. We want to run our constraints first and commit that transaction before we start adding data. So we'll do those in two different transactions. And here's where we do our batching. So this is a good technique, to break up our geodata frame. And this works with just regular pandas data frames as well. But specify some batch size. So here we're going to pass 10,000 rows at a time by default when we execute our Cipher query. Cool. So let's go through that for the nodes. And we have, how many nodes did we have? I think it's less than 20,000. Yeah, not very many. So we don't really need to batch these. If we're doing like, an entire state or whole country or world, like we definitely want to make sure we're batching those. We do 2 batches here. First one was 10,000, then the second was 8,000. That was all we had. Let's do the same now for our relationships. This might take a little longer. How many road segments do we have? 47,000. Okay, that's pretty quick. Looks like that's done. Cool. So I think we have our data loaded now. Let's switch over to Neo4j browser and Bloom as well to kind of explore the data. So here's a visual. Can I get all of this on the screen? Well, you get the idea there. You can wait. We have a version of this here. Yeah, there we go. So this is a visual that I created. This is the Boston road network. So this looks a little bit different than San Mateo. I was playing around with a few of these. I thought Boston looked the most interesting. I don't really know anything about Boston area to tell you what these neighborhoods and things mean, but I think Boston is kind of hilly, so maybe some of the disconnectedness has to do with some of the hills, perhaps. Not sure, but anyway, the neat thing about visualizations like this is that we can see the road network, sure. So these are all the intersections and the roads that connect them. But note that some intersections are bigger than others, and some are colored differently. So with graph visualizations like these, being able to style things like node size relative to centrality or some measure of importance is really nice, because it allows us to get a lot of information sort of at a glance. This was created with a tool called Neo4j Bloom, which we'll look at in a second. But let's go back to our Aura tab here and just kind of look at the data that we've imported thus far. So I'm going to hit the open button here, and this is going to launch what's called Neo4j Workspace. So I need to find my password that I saved somewhere. Here it is. So I'll put in my password. And this will load Workspace. So Workspace is kind of a combination of Neo4j developer tools that you may have seen before. Neo4j browser, which was a query workbench. You write Cipher queries, you get a little visualization. That is essentially what the query tab is. So we can do things like, say, call db.schema.visualization. And we can see, yep, we have a pretty simple data model. So we have intersection nodes, make that a little bigger. We have intersection nodes, and they have this road segment relationship connecting them. So pretty simple so far. But we created a constraint on the OSMID I think, on our address. And so that's why address shows up here, even though we don't have any address information. But we could do something like, say, match intersection, 10 intersections, and see we have some information about each intersection from the tags. If we double click, we can now start to explore our network. And that's kind of interesting, but this query tab is really for the case where we have Cipher queries and we want to just kind of interact with the results on a small scale. If we want to visualize the entire network or visualize it interactively, that's where the Explore tab comes in. So Explore, this is Neo4j Bloom, which is an interactive visualization tool. So this is useful if you don't know Cipher, if you don't want to write Cipher, or if you want to maybe configure how the visualization is configured and hand that off to less technical or maybe like analyst type persona. I think is a good way to think of who uses Bloom. You can also think of Bloom as sort of like the graph UI for your projects. So you don't have to create a specific UI. Kind of, depends on what you're building. In our case, we can pull in this road segment query. And so I got that just by clicking in the search bar, and this was one of the options. But Bloom uses this natural language like search. So I could say intersection, road segment, intersection, and so on. Very similar result. But note that we don't have to write Cipher to find data. And so by default, I think we're limited to 1,000 nodes in the visualization. I found a way around that. So I'm going to do Command A to select all, and then right click and expand all. And I'm going to do this a few times to get a bit more connected graph here. Depends on what kind of machine you have. When I use Bloom,
you can also define this. Do you know? If you click on the little slider at the top left, and then you click on the, where is it? There should be like a settings.
I don't.
Tab.
Yeah, I think the settings aren't available in Aura.
In Workspace. That could be it. Yeah.
Workspace,
Usually there's a little slider. I don't know.
Yeah, totally. If you're running this in like in desktop or locally, I bump it up to 10,000, and even then my machine's fine with more than that.
Yeah. Okay. Well, then it's a workspace limitation, but that's beta.
Yeah, and I mean it's helpful to have that limit in place.
Yes,
so
totally.
Bloom will use GPUs and WebGL, and some machines are less capable than others and get bogged down a little bit.
Yeah.
But my hack for getting around that is to do the Command A, select all, right click, expand, and this will allow us to go beyond that limit. And I just want to get a little bit more connected graph than what we had. We can also pull in like one section or one neighborhood, but this will work. I think we'll see what we want to see. Do one more expand. And we can see that we're by default using this force-directed layout. And so you can see here that this is like a physics simulation. This is kind of the standard layout that we get with graph visualization. And this is sometimes useful. Clusters can sort of emerge and be identified. But we have latitude, longitude information for all of these intersections. And what I'm going to do is change to the coordinate layout. And so with the coordinate layout, we will use the location property that is a point, latitude and longitude, to see how this road network is actually laid out. And so this is starting to look a bit more like the map that we saw. If we go back to, got a screenshot from OpenStreetMap right here. Yeah, we can start to see. So like here's downtown San Mateo and the bay, and then here's the coast and Half Moon Bay. If we look at back at workspace, yep, you can see that we're missing a big piece because we just kind of loaded some a few thousand nodes at random. But we can start to see what that looks like. So the styling in Bloom allows us to do things like let's style relationships using rule-based styling. And this allows us to bind styling to property values. So we're going to say, let's use the length of a road segment. So the distance between two intersections. We'll use that to determine the size or the thickness of the relationship. And that's somewhat useful. So like the longer ones appear, thicker. We could do something similar for intersections. So what I did in this visual, where is it? This one of Boston, was I ran some of the graph data science algorithms. There's a really neat graph data science integration for Bloom that allows you to run things like PageRank, betweenness centrality, and some of the community detection algorithms. I think specifically this is Louvain to identify the different neighborhoods, and then style your Bloom visualization according to the results of those graph algorithms. We're using Neo4j Aura DB, which does not include GDS. We're using Aura DS that has the graph data science integration, or if you're using Neo4j Sandbox or desktop, you'll have another button here that would allow you to do some of the point and click graph data science. Combining that with the coordinate layout in Bloom for road networks, I think is really cool. What could we do on our nodes here for styling? Maybe street count. So if you have several, if you have 6, it's like a malfunction junction. So you have 6 streets coming together. That should be bigger. It's a bigger intersection, maybe. We could also compute something like degree or degree centrality or something like that. But let's give this a try. See how this looks. Yeah, I imagine there's not a lot of variety here, I think, because most intersections are going to be 3 or 4. There's a few that are 6. Apply. There we go. Apply the size. So you can see, yeah, there's not a lot of similarity, or not a lot of difference. I think a centrality algorithm would be better. And you can see these are kind of smudged together. So the coordinate layout lets us kind of scale things to move our nodes around. Cool. Well, anyway, that gives you an idea of how to use Bloom to explore our data. Let's jump back to our slides. And I think we want to talk about how we're going to add address data. Okie doke. So we have imported our OpenStreetMap data. Now we want to add addresses. So there are a few different ways to get address data or point of interest data. Originally, I had us going through both point of interest data and addresses in this workshop, but I think that's too much to cover in the time limit. So we're just going to focus on addresses. There is some address information in OpenStreetMap. You can certainly pull out addresses from it. One thing that I've found to be a little difficult about OpenStreetMap data is that there's not always the same schema of tags used. So it can be sometimes a little bit of a challenge to consistently grab the information you're looking for. But there is the Open Addresses project, which is really neat. It's an open data project that is collecting address information throughout the world. You can see their coverage area that they have now. And so I downloaded data from Open Addresses about San Mateo, and this is GeoJSON data. So we'll see how to work with that in a minute. And what we want to do now is add to our data model. So far we have intersection to intersection. We don't have this point of interest piece. We'll talk about that later, and we'll leave that kind of as a take-home exercise, perhaps. But what we want to do is add these addresses. And so for address, we have the different components of an address, so like the number, street, postcode, city, these sorts of things. And then we want to hook that into our road network. So we're going to, for every address, we're going to create a node. We have the latitude and longitude, so the location point property, as well as the text description of the address. And we're going to then find the closest intersection to each address and create this nearest intersection relationship to hook our addresses into our road network. Cool. So that's the plan. So that's the next part of our hands-on exercise component, is to go back to our notebook here and add our addresses. So I fetched the San Mateo County address data set from Open Addresses. It's GeoJSON, and it looks like this. Every row is a feature. And GeoJSON basically has two components. You have the geometry of the feature. That could be like a point, line, polygon, something like that. In this case, they're all points and have a single coordinate associated with them. But then we have properties as well. So these are key value pair properties that define some information about the feature. In this case, we have information about the address. So we're going to use APOC-load-JSON to import this GeoJSON file. So I loaded this GeoJSON file up on the web, and we're going to grab all those features, and then for each address, we're going to merge, so create a new address node if it doesn't exist, and set the location to be a point property with latitude and longitude, and the values of each address. Now, you note that this is mapped in a call APOC periodic iterate, and like kind of separated into two statements. What's going on there? Well, these GeoJSON files could be quite large, and we want to break them up into batches and commit them across multiple transactions. We don't want to just throw some huge amount of address nodes to create in one transaction. Neo4j is a transactional database, so it needs to build up transaction state. We don't want to inefficiently use memory to do that. So APOC periodic iterate allows us to break this up into two statements. The first statement is kind of your thing that's matching on all of the values. And then the next piece is what you want to run for essentially for each row that's returned by the first statement. and this gets batched using this unwind trick that we saw before, kind of behind the scenes. But we're going to do this in parallel, batches of 10,000. And then once we've done that, once we've created these address nodes, we're then going to find every address that is not hooked into our routing graph. So where we don't have this nearest intersection relationship. And in that case, we're going to find the closest intersection and create a relationship to it. And again, we wrap this in a APOC periodic iterate because there may be a lot of these. And we want to do these in batches. In this case, we're going to do in a batch of 1,000 because finding the closest intersection and creating a relationship is a bit more intensive than just creating nodes, where we can get away with about 10,000. And then once we've done that, we're going to create a full text index for our address node. We don't have the point of interest nodes yet. We're going to create the index anyway. We're going to use this for our search functionality in our app, which we'll see in a minute. But okay, so I'm going to run that cell to define my queries. And then again, we've seen this pattern. We define the transaction functions to run our Cipher statements. We create a session, and then we run them. So we got a little bit of an error there. I think we did a retry. And I see some folks are having some issues in the comments with output exceeds the size limit. That's a good one. And that was on the, looks like that was on the 00 setup that exceeded the size limit. I wonder that the size limit of logging to the notebook. I'm not sure what that error would be. I would have to look at that one. That's a good question. So this might take a while to run. I think we have a few 100,000 addresses that we're adding here.
We have a good question we could cover in the meantime. That just came in from Matt.
Great.
Pros or cons to create the index before loading the data or after loading the data?
Yeah, totally. Yeah, that's a great question. So, like we said, indexes help us to find the starting point of a traversal, typically. It means that we have an efficient lookup to find something by ID or something like that to find the starting point for our traversal. That doesn't come for free. There's an expense associated with that, and that expense is updating this index data structure. And so we want our indexes typically to be up to date. So as we're creating data, we want the index to be updated at the same time, so that if we then query to use the index to find the data we just created, that it actually exists in the index. But if we're creating a lot of data, that can slow us down because each time we have a transaction, we have to update the index with that new information. So I think it depends. If you need the index, so like for example, here we're doing this merge on address by using address ID. So here we want to create a constraint on the ID property on address that says, address ID is a unique field. Don't create duplicate addresses. We want to create that constraint, which will create an index before we start doing these merges, for two reasons. One is that it's going to be more efficient to find if this ID value for this address node already exists by going to the index. And that's what the constraint is going to use to find that. But then the constraint enforces that. Here, where we created this full text index, we did this afterwards because like this full text index is not helping us to import data. We're going to use this at the end in our web application to search for things. So I guess the rule in answer to the question is, if you need the index to speed a lookup or enforce a constraint, then like, yes, create it before you start inserting data. A case where you might not have a constraint, but you'd use the index during the import is if you're like doing a match on two nodes by name or ID value and then creating a relationship. That'd be a good place to create the index first before you do the data import. But if you're not using that index as part of the data import process, it's just going to add overhead and slow down your data import, then create it later. But if it's a constraint, definitely create that before you start doing those merges. Yeah, that's a great question.
Cool. Thank you, Will.
Cool. So that ran importer addresses, and I ran this last cell to add our full text index. And just to verify that, we can go back to workspace. Let's clear the scene here. And let's refresh our perspective as we have new data. Always nice to have a fresh perspective on life. So a perspective, you might be wondering what a perspective is. A perspective is basically a configuration of the data that we have in Neo4j to specify how we want to visualize and how we want to work with that in Bloom. So what node labels do we want to expose? How do we want to style them? What properties do we want to use? These sorts of things. And so now can we say something like address, that's nearest intersection, something like this. So we can see where our address nodes hook in to our routing graph. Cool. And these are kind of on top of each other because we're using the coordinate layout. We can switch to the force-based layout. Cool. There we go. This makes a bit more sense. So here are a bunch of addresses, and this is the nearest intersection for all these addresses. And we stored, you can see on the relationships, we stored the length or the distance from the address to the nearest intersection. Cool. So now we've got our addresses. So our data model looks like this piece right here. Again, we're skipping the points of interest for now. And now it's time to revisit routing a little bit. So we saw that airport example using the GDS, the Graph Data Science plugin. And the GDS plugin is great. It has several pathfinding algorithms. So like shortest path, Dijkstra, A*, but then it has a few others and it gives you more flexibility on sort of the factors that go into your pathfinding algorithms. But if we're not using the GDS plugin, we can still use some pathfinding algorithms that are exposed to us through APOC. And if we take a look at these, so this is again using airport data, but we saw the shortest path example. So shortest path from San Francisco to, Fort Myers, Florida. This is going to be the shortest path by number of relationships to follow, not necessarily distance or time. And so you can see we end up going from San Francisco to you know, is that like Boston or something like that, and then down to Florida, which is not the shortest path by distance. For that, we want shortest weighted path. So that's either Dijkstra's algorithm or the A star algorithm. So with Dijkstra, we're taking into account the weight or the property from the relationship that measures our cost, and this can be distance, it could be time, it could be like cost of the fare, it could be some function that's a number of these things together. In this case, we're looking at the distance property on the relationship. And so in this case, instead of this circuitous route, we go from San Francisco with a layover somewhere, is that Texas, Dallas maybe? I don't really know Texas geography. And then to Fort Myers. A star is an improvement on Dijkstra's algorithm. Usually just means that it's going to find your path faster because it's going to prefer expanding routes that get you closer to the final destination. So with A star, we add a heuristic. In this case, the distance to your final destination. Like, are you getting closer to where you actually want to be? And that typically allows you to find paths faster. And so you can see in this example, we prefer a route that gets you, is that North Carolina maybe? So it gets you closer to your destination first. A star is typically used in, you know, things like video game pathfinding. If you need to get around some obstacle or something like that, it's typically more efficient than Dijkstra. Anyway, both these algorithms take into account shortest weighted path rather than just the number of hops between your destination. Cool. So in the time we have left, let's switch over to our web map with Leaflet, and we'll see if we can get our routing app up and running. So we're going to use Leaflet as our map library. If you haven't used Leaflet, Leaflet is a pretty light JavaScript library for creating web maps. You can use various kinds of tiles. We're going to use the OpenStreetMap tiles. It allows us to do some drawing and some interactive bits as well. Cool. So for the next piece, I think this is our final piece of the hands-on components. We're going to open in the web directory this address routing.html file. I put all the HTML and JavaScript in one file just to make it easier to keep track of. And what we want to do is update the Neo4j AuraDB credentials. And then in a web browser, we want to open this address routing.html file. So you might want to run a web server. You do that using Python. This works in code spaces. Code spaces will expose a port for our web server, which is quite nice. And then we can search for routes between two addresses. And while you're looking at that, take a look at we'll of course go through all the code, but take a look at the query that we're using to execute the routing logic. What algorithm is it? And can you figure out a way to improve that using, say, for example, the A star algorithm? Cool. So those are the things we're going to look at. I'm going to switch back to my code space environment, which is right here. And I'm going to go to web and address routing. And again, like I said, I put this all in one HTML file with the JavaScript kind of inline so that it's easier to keep track of. Let me zoom in a little bit. So there's some, HTML boilerplate stuff here. We're pulling in some CSS for Leaflet and one of the Leaflet plugins that I think we're not actually going to use in this case. And then we pull in some JavaScript for Leaflet as well, and then the Neo4j driver. So we've used the Neo4j Python driver. Now we're in JavaScript land, working with this web app. So we want to use the JavaScript driver, and the Neo4j JavaScript driver comes in, I guess, two flavors. There's sort of like the node version, and then there's the browser version. And so in the browser, we're going to connect using WebSockets to Neo4j. Got some basic styles here. You'll notice there's some CSS for autocomplete and inputs. We'll take a look at what that's doing in a second. And then here down on line 119 is where we start our JavaScript code. And so first thing we'll want to do is replace our connection credentials to Aura here. So I'm going to my .env file, grab my connection URI to Aura. Which goes here. And then the password, which goes here. So that'll allow us to connect to Neo4j using the Neo4j JavaScript driver. And then this is a function that handles our autocomplete functionality. And I grabbed this just from an autocomplete JavaScript tutorial for the most part. And so we can see basically as we're going through the autocomplete, we're going to use the full text search, a full text index rather, that we created in a previous step to execute our search operation, and then we're going to leverage this autocomplete functionality to add those options for addresses that match whatever we're typing in. So it's just some JavaScript to handle that autocomplete functionality. Now we're rendering our map, and when we're ready to find a route between 2 points, the first thing we do is we look up the source and the destination. In this case, these are going to be address nodes. And we find the nearest intersection. So we call those source and target. And those we pass to Dijkstra, or source and target, following the road segment relationships, using the length property on the road segment relationships as our weight for our shortest weighted path. And then we return basically this is just going to be a list of latitude, longitude pairs for each intersection. So we run that query. And when the results come back, we then create a polyline in Leaflet using the coordinates and add that to the map as well as the markers for our source and destination. Cool. So let's see that in action. So I updated on, what is this, line 120? Yeah, 121 and 122. I just put in my connection credentials to my Aura instance. And I'm going to run python-m http.server. This is just going to start a local HTTP server, and CodeSpace is going to expose that port. So when I hit open in browser, it's going to connect to my CodeSpace environment, serving that content. So I want the web directory, and I want address routing.html. So this should show us our map. Cool. Here's our map. Make this a bit bigger. Yeah. So here we're focused on San Mateo. And let's find the route from, see, as we start typing here, we get autocomplete, which is pretty cool. How about 32 Hillsdale Boulevard? I was looking for I'll give you 31 Grand Boulevard. Sure, let's do that. This is close to where I used to live in San Mateo, and we want to go to the Neo4j office, which is 111 East 5th Avenue. Yeah. You can see how that autocomplete works. It's using like case-insensitive fuzzy matching to match against the full address property as we start typing. Now I hit route to find the route between these two locations. And as I zoom in, here's 31 Grand Boulevard, and here's the shortest path to the Neo4j office, which is down here in downtown San Mateo, right by the park. Cool. So that is that's our basic web app for routing that we created. Let's find a longer route. How about somewhere in Half Moon Bay? Sure. Display Half Moon Bay to we're in Burlingame, maybe. Random. This will give us a little longer route to explore. Did that one pop up? Did we get an error on that one? What happened on that one? Object. We get a route. Why didn't we add our route? We have it. Something went wrong on that one. Let's go somewhere in Burlingame. We're not fully connected to everywhere in Half Moon Bay, maybe. There we go. So that gets us over the hill. So a little bit more complex route there. Cool. So we're about out of time, but really that is essentially what I wanted to cover. There is an option, the take-home option for you to add the point of interest data, so that our web app is set up and our full text index and everything is set up to handle point of interest data. So instead of just addresses, we could also search for like, I don't know, such and such a park, or a San Mateo library or whatever, and then those will show up in the autocomplete as well. And there's a bit that kind of points you at how to do that using this example. So if you follow the steps in this notebook for importing points of interest, then you can also combine that with point of interest data as well as addresses. That was kind of one of the main points of using that full text index, was being able to have one index that searches both address nodes and point of interest nodes, which is pretty useful. Cool. So slides and code, all the resources are available online. And Alex, I don't know if we have a few more minutes. Should we take questions if there are any, or what do you think?
Yeah, I was just saying maybe we can quickly do the 2 more questions. I think I'd like to add and to cover before we close. I think these are interesting ones. The one is kind of like a follow-up to the indexing. Deep asks, so when we delete the index and recreate one, do we need to, sorry, this is the important bit. Do we need to delete the index and recreate whenever we add new nodes or relationships relating to the index, or is there an update option?
Yeah, good question. Yeah, so on most of the indexes by default, they are synchronously kept up to date. So when you add data, the index is updated in the transaction before the transaction returns. I think that's the default behavior. That's not always what you want. Like sometimes you don't care if your index is up to date. And so there is an option that you can set to have those indexes asynchronously update, which means in the background, they'll just sort of update after the data has been added. So that's a configuration option. Again, totally depends on what you're doing, but no, you typically don't need to drop an index and recreate it after you've added data. Typically those are kept up to date, either synchronously or asynchronously.
Cool. And then from David, is there a best practice way to avoid having to give away your Neo4j credentials in the HTML?
Yeah, that's a good one. So if we look at where's our code? There? No, here. Yeah. So if we look at here, we are using a client-side JavaScript application to connect to Neo4j. We've kind of hard-coded our credentials here to be able to do that. I mean, there are some things you can do to kind of obfuscate this. But I think, fundamentally, if we're connecting directly to the database from a client's application, these credentials are going to be in the client application. Typically, what you would do is you would build like an API layer or something that sits between the web application and the database. And so like this logic would live in a API application that's talking to the database, and your like JavaScript app is talking to the API. So you're not seeing those credentials. It's kind of a quick and dirty way to get things done for a workshop. But yeah, I haven't really found a great solution to that. There are other auth options for Neo4j, like single sign-on and things like that. Perhaps you can pass just a key or something like that. But yeah, I think fundamentally, if you're connecting to the database directly from the client, those credentials are going to exist on the client.
Cool. And then maybe one more from Eshwar, because you showed these various algorithms. Is there a way how to map the way in a way depending on your needs? So let's say I want to showcase a specifically very safe path, or I want to showcase a fuel saving pathway, or how do I could I showcase more options and then pick one that suits best?
Yeah, totally. So here we're using Dijkstra's algorithm to optimize for distance. So our cost function is purely distance. Your cost function can be whatever, right? It's like if it's a walking path, I maybe want to not go on like highways and things like this. So I can be more complicated in how I'm specifying, the pattern that defines the path that I'm looking for. So I can say like, don't follow highways, only follow, like bike paths, things like that. Our cost function could take into account elevation. Like if I'm biking, I want to like minimize elevation changes, perhaps something like that. So yeah, those are things you can do by kind of extending, I guess, either like what defines the path connecting your source and destination, or by what defines that cost function, and how you're thinking of what defines that that weight. So really, within those two sort of parameters, you can come up with a lot of really interesting, complex pathfinding algorithms for sure.
Yep. Okay. I think we are a little bit over time, so let's close it here. Again, the the slides will be available. I'll share them with you afterwards. The video, obviously, also, so you can watch again later. Check out the GitHub repo in your own time, and click through to build the the web app again if you today just watched when you did it live. If you interested in the next training series, here's the schedule. So in 2 weeks' time, we do Spring Data Neo4j. If you have in the meantime any questions, any feedback, any comments, then check us out on our community page, community.neo4j.com, or in Discord, discord.gg/neo4j. There's a Graph Academy, maybe shortly talking about this. So if you are in your learning process and want to do another training session or something else in the data science world or in the database world, there is tons of trainings and modules available on the Graph Academy page. So just go to graphacademy.neo4j.com and check that out. Any other pointers from you, Will? I'll quickly look for that Graph Academy link.
Yeah, I think, we mentioned Neo4j Sandbox a couple of times. Some of the same data sets are now available in Aura as kind of like a getting started experience. There's specifically an OpenStreetMap example in Neo4j Sandbox. So if you're looking to dig deeper, specifically into geospatial data, that's a good sort of interactive place to go.
Yeah, that's true. Yeah, and with that, thank you very much. Thank you for your questions. Thank you, Andreas, for helping out with Q&A. Thank you, Will, for presenting and for this great demo and hands-on session. I liked it a lot. I think it was good. And yeah, I hope to see you around in either on the next training series in 2 weeks' time or another live stream. Just so you know, there is one scheduled for tomorrow with Donovan Bergin, where we talk about SchemaSmith, a Neo4j application to help build your schemas or maintain your schemas. So could be interesting, maybe. Check it out. It's going to be on YouTube tomorrow, 5 p.m. Central European time. And yeah, with that, I wish you all a great rest of your day, rest of the week. Take care, everybody, and see you soon.
Bye, folks.